Well, I want to welcome everybody to the wonderful world of the cerebral cortex. I'm sitting over here in the Media Center on University Avenue. I'm going to try a different place to record. One thing is I'm going to have to add the pointer later on because in this particular program the mouse doesn't show, so I'm going to add pointers later on. But this is really a super important lecture and a really interesting lecture. This is a lot better than brainstem and spinal cord, I can tell you, because we're going to be talking about the cognitive regions of our brain, the cerebral cortex. And you can see up on the upper left and right, you can see a medial view of the hemisphere and a lateral view of the hemisphere. And on that lateral view of the hemisphere, you can really see the lateral fissure, huge lateral fissure, so rostrals to the left, caudals to the right. You can see the temporal lobes, different lobes, occipital lobe way in the back, frontal lobe. You can see our friend the cerebellum and the brainstem. In the lower right, you can see a very, very famous story. And you can see there's a picture of a student in there from the past and in the eyeball. And this was Phineas Gage, who had a big spike go right up through his frontal lobes, and he was the first prefrontal lobotomy. On the left, you can see a guy who's just kind of feeling the different bumps and grooves on a patient's head. And this is phrenology, trying to tell different areas of the brain underneath by the bumps and the grooves. Well, we've moved a little bit beyond that, but not too far. I like to show this slide. You can see one area there. There's an area of the brain for conjugal love, and there's another one for self-esteem. And I like the one lower left there. It says emotiveness, and it's got Cupid, I think, with his bow and arrow. Then there's a relatively full-looking person there called, in the drawing of somebody who's put on a few pounds, called alimentiveness. So you can just see this is just a joke, but all the different cortical areas, it's true that different cortical areas, though, have different functions. And, of course, look different as far as their cells and their myelination is concerned. First person to ever look at all the different areas of cortex was Brodmann. I won't try to pronounce his first name, Corbin Ian. And he basically just sectioned the brain. And I think you've heard a little bit about this from Dr. Ulrich. He sectioned the brain, and then he stained the brain and looked at the different cellular layers and myelination patterns. And then he just identified each cortical area based upon what we call a cytoarchitecture. And he divided the cortex into many, many different areas, which are shown in the next slide, I think. Yep, this is a good picture of the left hemisphere. And many of these areas we should know already. And I think the first ones you ever heard of were areas 3, 1, and 2, the somatosensory cortex. You remember when we were way down on the spinal cord and we were talking about dorsal columns and ALS. We were talking about eventually the somatosensory information would come up to 3, 1, and 2 in cortex. Of course, they can only reach the cortex by going through the thalamus. So 3, 1, and 2 we heard about. Then we heard about area 4, primary motor cortex, or we also call this M1. This is where those big cortical spinal cells lie. The biggest ones, of course, are called the BET cells. And this is the origin of the cortical spinal tract, area 4. We also can call this precentral gyrus because it's in front of the central sulcus there. So between area 4 and 3, we can see the central sulcus. Rostral to area 4, we're going to see the premotor area. You can see 6 there. If we're on the medial wall and a little bit of the lateral wall up where the number is, we're talking about SMA, supplementary motor area, and that's good for internally generated movements. If we move out lateral there, it's not really indicated. We get PML for externally generated movements. You heard about area 8. Those are the frontal eye fields. You heard about the frontal eye fields from me. You can remember that the left frontal eye fields would move the eyes together to the right. So if you had a lesion here in the left area 8, the eyes are going to be deviated to the left. Remember, just caudal to this would be the primary motor cortex. So if you had a big lesion of 8 and area 4, you could have a hemiplegia and some problems moving your eyes. The big arrow there is to the lateral fissure. We've heard about 41 and 42, primary auditory cortex, from Dr. Populin. You've heard about area 17, primary visual cortex, from Dr. Ulrich. You've heard about 5 and 7 from Dr. Ulrich, posterior parietal cortex. The angular gyrus, number 39 there, you're going to hear from me today. I got a slight cough, so I may be coughing in and out, but maybe we can get rid of that when we edit this. Let's look at the medial wall. What jumps up on you here would be the area 6, SMA, on the medial wall. Now here there's no PML. We can just see SMA on the medial wall. So remember, there's a planning area on the medial wall, because the medial wall is going to get its blood supply from the anterior cerebral, while the lateral wall is going to get it from the middle. You can see some area 4. You can see some 3, 1, and 2 in the somatosensation. And remember, the part of the body that's represented here on both the motor and sensory side would be the foot, lower leg. You can see the calcarine with a big red arrow, area 17, dividing the upper bank and the lower bank. And remember, the lower bank is looking at the upper visual field. The upper bank is looking at the lower visual field. Caudal, that is to the right, would be more related to central vision. Peripheral, rostral. Rostral along the bank, there would be peripheral vision. You can see a bunch of numbers there you haven't heard about. Some of those we'll talk about today. Now, the first things we're going to talk about are 2 areas. One of them is called Broca's area, which we call the inferior frontal gyrus. You can see there 45 and 44. The other area we're going to talk about is Wernicke's area, back more in the temporal and the parietal areas, and we usually talk about areas 22 and 40. You can see the auditory cortex there is 41 and 42. Now, Paul Broca was the first to describe an aphasia, and we would call this a motor aphasia, Broca's speech area on the inferior frontal gyrus. He had a patient come in, and the only thing the patient could say was tan. So the patient would, during the entire examination, would just say tan, 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 tan. And Dr. Broca had never seen anything like this. Well, later on, when the patient died, who was always saying tan, 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 they looked at his brain and they saw a huge lesion that you can see there in the left inferior frontal gyrus. And this has since then been called Broca's speech area. What's interesting about this, you can see a clinician talking to a patient down in the lower left of this, and the clinician says, "What can you tell me about the stroke?" And Mr. B can hardly say anything. You can see he says, then he sighs, So he's having very difficult time telling words, and he's extremely frustrated. And he has kind of this telegraphic speech, but very difficult to get the speech out, and he's frustrated. And many times these Broca's patients, because it's usually on the left side, almost 70 or 80% on the left side, sometimes the lesion can get into the motor cortex, just caudal, and these Broca speech patients can have a contralateral or a right hemiplegia. Here you can see a comparison of Broca's aphasia over there on the right with another aphasia called Wernicke's aphasia. You can see that here we're getting much of the parietal and temporal lobe. And you can see the physician who described Wernicke's aphasia down in the bottom right, Carl Wernicke. Now let's contrast the Broca's and the Wernicke's aphasias. First of all, they're in different locations, but look at what the clinician says and how the patient answers here on the left side. The clinician says, "Tell me about your work," and Mr. W just takes off. And remember, the Broca's patient, he can hardly get anything out. He was extremely frustrated. But this patient with a Wernicke's aphasia just starts talking like crazy. When I grew up in the Army, this was my whole fife. I used the wrong word there, called a paraphasia. I was in the Army and the war and everything else under the sun and everything. This is what we call very fluent. The Broca's aphasia is very non-fluent. This is very fluent. The person has fluent speech, talks like crazy, but and is not at all upset because he really doesn't know what he or she is saying, and using lots of terms, paraphasias, saying hike for pike, can't comprehend that he or she is screwing up. So this would be a Wernicke's aphasia versus a Broca's aphasia, and there are different parts of the brain. One's in the frontal lobe, inferior frontal gyrus, areas 44 and 45. The other is more in the parietal temporal lobe, around the auditory cortex. You see 41 and 42. That's getting input from the medial geniculate body, so that's the primary auditory cortex. So it's the area surrounding it, 40 and 22, that's involved in Wernicke's aphasia. So we talk about an area of the brain on the left side, 44, 45, that's involved in production of speech, and we talk about an area of the brain in the more caudal part that is more receptive in speech. Now, this is a great slide because it shows a dissection that I did. It shows what is called the arcuate fasciculus. And the arcuate fasciculus connects Wernicke's with Broca's. And it's a bundle of axons. Now, a bundle of axons that interconnects two different parts of the same hemisphere. It doesn't cross like the corpus callosum. Same hemisphere is called an association bundle. And the arcuate fasciculus is an association bundle. And there's some classic signs that happen when you have a lesion there of the arcuate fasciculus. It's called conduction aphasia. Now, in these patients, comprehension is okay because Wernicke is not damaged. It's the connection between Wernicke's and Broca's. So comprehension is okay. They're very fluent, but they can't repeat what they've heard. Now remember, in a Wernicke's, comprehension is bad because they've lost that receiving area. It's still fluent, and they have the word salad with the paraphasias. Again, they can't repeat either. In a Broca's, up in front there, in the inferior frontal gyrus, they can comprehend, but they're not fluent. And therefore, they kind of have this dot, dot, dot telegraphic speech, but they also can't repeat. This is a good slide. This is something similar to this is in your book. This is classic, very, 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 very classic national board. You'll see this on the national board. And most common cause for these aphasias, Broca's aphasias, Wernicke's aphasias, is usually stroke, but you can also have, motorcycle accidents, trauma, that'll also give this to you. I think this is an interesting slide. You might say, well, how do they know what's on speech areas are on the left side and all those kind of things? Well, they can put one side of your brain asleep and see what you can do by injecting this sodium amytal into one of your carotids. It's called the WADA test, and they like, for instance, if somebody's got a brain tumor in one particular part of their cortex, right or left, they can do the WADA test first to see where their speech is. It could be that in some people, speech might be on the right side, not that many. Most people, it's on the left. And I knew of a patient who had speech bilaterally. So by doing this WADA test, they can find out where speech is localized in each patient's brain. This is something cool I thought you might like to determine whether or not you're right or left-brained. And I took this test, and it looked like, I did. I turned out to be 10 left, 8 right. So take this. This isn't going to be on the exam, but it's kind of interesting. I thought it might turn on some of you guys and gals. Now I'm going to talk a little bit about split brain preparations. It's kind of interesting. This is an interesting slide that I got, but it's good for one thing. You can see that person's looking straight ahead at that funny-looking red star. So this is important for the next slide. Well, first of all, I suspect I should tell you about the great commissure, the corpus callosum, that interconnects the two hemispheres. It's called the corpus callosum. Now, remember, this is a commissure because it interconnects the two sides of the brain. We saw the arcuate fasciculus That's an association bundle. Those interconnections between parts of the brain remain on one side. They don't go to the other hemisphere. And you can see those red arrows are pointing to a huge myelinated bundle called the corpus callosum. This is another view of it. A frontal lobe is to the left. The visual cortex occipital lobe is to the right. And you can see the corpus callosum there. You can see some other myelinated bundles like the fornix. And then there's a bundle there that I've labeled the cingulum, which is just a bundle under the cingulate gyrus that we'll talk about later in the course. You can also see some what we call U-shaped arcuate association fibers. And these are just little connections between one gyrus to another. So you can have these little U-shaped arcuate. You can have something like the corpus callosum that connects the two sides. You can have the cingulum, which is an association bundle connecting parts of the brain on the same side, and we can have the arcuate fasciculus, which we showed in an earlier slide, which is also an association bundle. This is a great slide, just showing the corpus callosum and a little thing on top of the corpus callosum called the indusium griseum. But look at all those bundles of axons connecting the two sides of the brain. This is a great picture. This shows another one that used to be in your course book, but it just shows fiber bundles connecting same side of the brain and association bundles and corpus callosum in the case of a commissure. Now, you should remember your visual fields from Dr. Ulrich's lecture. You know the things on the left half of the visual world, like that basketball or baseball there, eventually reach the right cortex. And things in the right half of the visual world, like that pencil, reach the left half. And you know they go through the lateral geniculate body. You know all these kind of things. Now, if you were to interrupt or have a section right down the middle of that brain right there so that the right hemisphere couldn't talk to the left hemisphere, remember now the left hemisphere is the one doing the talking. So if you had somebody fixate straight ahead there and you flashed that ball there, out there, it would eventually go to the right hemisphere, and they wouldn't be able to say it's a ball because it can't go from the right hemisphere through the corpus callosum to the left hemisphere where all the speaking takes place. However, if they saw that pencil up there flashed in their right half the visual world, it would eventually go to the left hemisphere, which can talk. So just keep that in mind that in this particular case, there's a lesion right down the middle there in the corpus callosum, so the right hemisphere is no longer connected to the left hemisphere. And just remember, the left hemisphere is the one that does all the talking. Now, if you flash that ball in the left half of the visual world out there and it went up to the right hemisphere, and you asked them to reach out with the left hand for either a pencil or a ball, they're going to reach out with their left hand for the ball. So here's another example. Let's just say down here in the right, you got a man's face and a woman's face, and this is in a split brain patient. So if they flashed the man's face, it would go up to the left hemisphere, and they could say it's a man's face. If they flash the woman's face, it's going to the right hemisphere, and they can't talk. They can't say it's a woman. But if they had to reach out with their left hand to a picture of a man or a woman, let's see, I guess they'd have to feel the man or woman. I didn't think very carefully about that. But let's see, they flash the woman, and it goes to the right hemisphere. What would they do with their left hand? Well, that's kind of difficult. I can't say they'd reach for the woman, can I? Well, you have to think about that. Or you can ask Dr. Bell during the lecture. Now, here's a big syndrome that everybody's got to know. Look at those lesions up there in the right. All these lesions, there's a yellow lesion and a purple lesion and a green lesion, and then there's a pink one. They're all on the right hemisphere. So keep that in mind. None of these are on the left, like Broca's and Wernicke's. So they're on the right hemisphere, and they're kind of in the occipital and the temporal and the parietal lobes. Most of them are. Now, if you have a stroke in these areas, usually a middle cerebral artery, and we haven't had blood supply, but we'll get to it. We're talking about damage to the right hemisphere. We get something called contralateral neglect. Many of them will get a contralateral neglect. Now also don't forget, some of these might have a left hemiplegia because we're talking about lesions that occur in the right hemisphere when you get contralateral neglect. What you see here is that patients are just going to ignore most things on the left side. In many cases, they'll ignore lesions growing on their, on their left arm and leg, hemiplegia. They just pretty much neglect the left side. And let me show you a couple of instances here a couple things I want you to know. One of these is called anagnosia, where with a lesion in the right hemisphere, the patients are unaware of any kind of severe deficit or disease or anything on the opposite or on the left side. There's another thing called extinction that happens. You see down the bottom, the patient ignores their left side, but once in a while they may detect a stimulus there. Remember, they can see there, but this is a higher level thing. So they're ignoring the left side, but once in a while they detect a stimulus on the affected side when it's by itself. However, extinction occurs when the stimulus is presented with another one's on the other side. So they can see it if it's just by itself on the left, but you put one on the right and it's gone, and that's extinction. Allocuria and alesthesia are kind of very similar. In allocuria, visual stimulus in the left might be detected, okay? But it's wrongly perceived as being in the right hemispace. Alesthesia is kind of similar in that the left field visual stimulus can be perceived at the wrong location within the left hemifield. So alesthesia, you're going to see something in the left hemifield, but it's in the wrong location. Allocuria, you're going to something's placed in your left visual field you might detect, but it's wrongly perceived as being presented in the right hemisphere, right hemispace. So here, this is something called neglect. It almost 100% occurs. Yeah, well, you never say 100, but most of the time it occurs with right hemispheric lesions, in contrast to the Broca's aphasia and the Wernicke's aphasias, which are lateralized to the left cortex. This shows a few more interesting things about neglect. You can see that in the upper drawing there is a fellow who's doing a self-portrait. And he had a stroke in his right temporal parietal occipital lobe, and he's looking in a mirror there, and he's painting himself, but he's ignoring the left side. And then later on, you can see it comes back. You can see down the bottom with these right hemispheric lesions, you see a person, you say, draw this model of a clock, and they pretty much ignore the left side. You can see the house, they're ignoring the left side of the house. This again is with right hemispheric lesions. This is neglect. This is very important for you to know. This shows a cancellation task where they're supposed to cancel out these circles. You can see they're completely ignoring all the circles on the left, and they're canceling out some on the right, because that's what they see, but they don't see the circles on the left, so they can't cancel them out. This is kind of cool. Healthy control, if you're asked to bisect that line, you're going to put it right in the middle. But a patient that's having problems with neglecting the left side, so the left side is much smaller, so the middle of the line is further to the right. And this is what we call the star cancellation test, where the patient's supposed to go in and circle the stars. And if it was a patient who had a big right occipital temporal parietal lesion, they would circle only the stars on the right. Here's somebody even looking. You see down at the bottom, they're searching for the letter T's and L's. They're looking for T's and L's, and even their eyes are only searching the right side. They're completely ignoring the left side. Hemispatial neglect. Other symptoms of contralateral neglect that you might want to know: they bump into objects on the left side. The classic story I heard when I was a graduate student, that people didn't groom the left side of their body for years. I once saw a picture of a dog eating out of his or her bowl, and was only eating the food on the right. And so these are just some good ones that some of you might remember as you go on into clinical years. Now, another syndrome I want you to know is called Alexia. That means you can't read, without agraphia. Agraphia means you can't write. Now, so this syndrome is called Alexia without agraphia. That means the patient can't read, but they can write. And to understand this, we have to think about a section, horizontal section, like that black line there, through the cortex. And you can see the big arrow there is cutting through part of the caudal part of the splenium of the, it's called the splenium of the corpus callosum. It's also, you can also see the black line going back through the visual cortex. So what we're going to do here is we're going to show a slice like this, but this is the right cortex. I hope that you can see that. And we're going to show a slice like this and emphasize what's happening on the left cortex, which we should be able to see in the next slide. In the right there, you can see we're using our typical MRI left-rights, where right is on the left and left is on your right. And you can see I have a circle down there that's involving the left area 17, visual cortex, and some of the splenium of the corpus callosum. Now, what's going through that commissure is information from the other area 17. So if we had a big lesion down there on the left that got the left area 17 and all of it, so a big whopping lesion of left area 17, so you're not going to be able to see anything on the right. But we're also getting the splenium of the corpus callosum there that enables information from the right area 17 to get into the left area 17. The right area 17 is okay. It just can't get to the left side of the brain. Now, what would happen here? You can go over there to remember your visual fields. I put a little reminder here for the up in the upper part of this. You can see that the left, if you look down in my drawing, the left area 17 is receiving information from the opposite half field. The right area 17 is receiving information from the opposite half field. And I'm just showing the basic diagrams up there on the left, even though the right and left is flipped. Now, don't forget, Alexia is an acquired deficit in reading, agraphia, acquired deficit in writing. So this is called Alexia without agraphia. It's also called Grossmans Syndrome, and Grossmans described this in 1892. So you might see it sometime when you're on the wards as Grossmans Syndrome. So what you have is a lesion of the left area 17, so you're going to have a right homonymous hemianopia. And this is usually due to an infarct of the posterior cerebral artery. But you should at least understand that you can't see in the right half field. So because you have a lesion of the left area 17, you have a contralateral or a right homonymous hemianopia. So nothing's getting through from the right side up into the left cortex. Now, if you also interrupt the splenium of the corpus callosum, you can't get information from the right hemisphere, which would be the left half field, over there into the left. And you know you got to get over to the left side to eventually work your way into Wernicke's and Broca's to speak. Okay? And you're also going to use Wernicke's and Broca's to read. And that's something that we didn't mention when we talk about Broca's and Wernicke's, but you also need these areas to help you read. Okay, so now what we would have here is that the patient here has a lesion in the left area 17, so he can't see anything over there in the contralateral half field. He or she can see things in the left half field, but they're going to the right visual cortex, and then they have to work their way over into the left side to be able to read. So you can see that with I'm just going to read it. The patient can write normally. What does that mean? That means that other areas of the brain that are not involved in this lesion are involved in writing. Can't read? Well, the only place that the person can see is opposite the right half field. But to be able to read, you got to get the right hemisphere. But to be able to read, you have to get it from the right hemisphere over into the left hemisphere. And that can't get over there because you have a lesion of the splenium of the corpus callosum. So this is called Alexia without agraphia. And this shows a couple things here I want you to see. I want you to see that lesion there. You see those two MRIs? You can see the lesions there. I'm pointing to them with red arrows, and they're the lighter areas. And you can see that they're nipping the splenium there of the corpus callosum, but they're also getting area 17 at different levels. And the diagram over on the left, I'm just trying to help you orient yourself. So these people have the ability to write a passage, but the inability to read the passage back. They can recognize letters as, N is N. They have the inability to associate individual letters with a sound, like N sounds like ENN, and an inability to read a word as a whole. So let's go back one. This is called Alexia without agraphia, and you're probably going to see this on my exams, and you're probably going to see it on national board exams. It's pretty interesting because it relates anatomy to behavior and to reading and writing. Now, Grossmans Syndrome, I'm hoping that Dr. Bell can tell you more about this. It's a lesion on the left side in the angular gyrus, and you can see I blackened it out there. This is called area 39. And this was described by Grossman. I've never seen really good explanations of it, like with what we were just talking about. But Grossman's has some classic signs and symptoms that I think you should know. And they're listed over there on the left. There's a right-left discrimination problem. Finger agnosia. That's pretty interesting. The subject was asked verbally to point to an index, middle finger. Can't do it. It's a finger agnosia. You don't know the finger. Agnosia is you don't know. There's dyscalculation, acalculia. Can't count. You can't write. Dysgraphia, agraphia. So you can't calculate, you can't write, you have finger agnosia, and you have this right-left discrimination. This is all Grossmans, usually on the left. That'd be probably mostly middle cerebral, maybe some posterior cerebral. Area 39 of Brodmann. And I've got a little more information here on coming up. It's kind of interesting. Here's just they do 9 tests for the finger agnosia. So in the situation 1, the subject's asked to indicate which finger was used in different situations. For example, it was asked which finger is used to indicate direction, hitchhike, things like that. These people can't do this. Another situation, the subject asked verbally to point to the index, middle finger of either hand, and usually the hand is behind them, and they have to point to it behind them. They can't do this. And then the right-left confusion, I'll show the next slide here, where the index finger is pointing a certain direction, and they can't do this. And it's kind of interesting. If you go through those, look at them real fast and try to say which way the index finger. I mean, really do it fast. I think it's pretty hard. So this is all Grossmans syndrome. Now here's a lesion that I found on the web. You can see the angular gyrus over there on the left, and here I found an article about somebody who had Grossmans, and you can see I've shown the lesions, and you can see the one on the right. It's a whitish area. That's the lesion, and they called it a left subangular. In other words, it's getting the white matter underneath the angular gyrus. Now you can see that parasagittal view. It's harder to see, but it looks like a little L or hook there of white matter there at the tip of the pointer. So it's interesting to see where the lesion is. Relate these two MRIs to what you're seeing over there in a left view of the hemisphere. It kind of gives you a better feeling for how this area looks in 2 MRIs of different orientation. Agnosia is just pretty straightforward. It's without knowledge. And I'm going to talk primarily about visual agnosia. Here's a lady that she looks at those keys, and she can't tell, she can't tell that they're keys because she has a lesion in her brain that's resulting in visual agnosia. Now, it's involving visual areas, so she can't tell what they are. She can't tell you what they are. Now, you can see she picks them up, and all that somatosensory information that's coming in her hand and going up to 3, 1, and 2 is going to tell her that they're keys. She can tell by feeling them. She could probably even, if you jingled them, she might be able to tell they're keys, but she can't tell by looking at them. I put this on a quiz once. to the OT-PT course, and I hadn't put the labels down there. Can't tell by looking and can't tell by feeling, but we had talked about this, and this was the most missed question on the quiz. So think about what this picture shows. Now there are a couple different types of visual agnosia. We break visual agnosias, and that's the only type I'm going to talk about, into aperceptive agnosia and associative agnosia. Now, aperceptive agnosia usually is found with lesions in the occipital temporal lobe on one side, and if you have the associative agnosia, you usually have bilateral lesions. This is one place where I can't tell you that a lesion of X gives you these particular agnosias. Now, an aperceptive agnosia is a form of agnosia in which individual features cannot be integrated into a whole perceptor pattern. And I would call this kind of a lower level agnosia. Associative agnosia is a much more higher level agnosia, and I'm going to show you some differences between the two. Now, if a patient has an aperceptive agnosia, you can see that they can't, their vision is fine. Like if Dr. Heatley came in and examined them, their vision is fine all the way up to area 17. It's a higher visual cortical integrative area that has the damage. And if it's an aperceptive agnosia, they have difficult in the perception. So you can see if they were to draw ABX034, they can't do it. So they have an aperceptive agnosia. If you look at the next one to the right, you can see all those different types of fruit that are in one drawing kind of camouflaged. And if they have an aperceptive agnosia, they can't draw the pear and the grape and the banana, the apple. Oh, those are cherries. The grapes, I don't know what that thing is under the grape. Looks like then a tomato and an orange. All right, they can't do that. Also, you take a bucket, like that bucket, turn it upside down and give them an unusual view. They can't do that. They wouldn't be able to identify the bottom part of that as a bucket if they have an aperceptive agnosia. Then they're unable to do what we call the incomplete figure test. Now, I know that most of you know what that incomplete figure test is, but the way they do it is they take that figure and then the next figure is a little more of what it is. And then the next figure is even a little more of what the final figure is. So now, when I look at that, I see a cow. I really do see a cow. But I know that most of you are not going to see the cow like me. But, you know, I've been teaching neuroscience for over 35 years, and, you know, I can tell that that's a cow. And you see the first one there is what I saw. But I can then bigger, but there's the cow. Now, somebody with aperceptive agnosia would not be able to tell the cow probably till the cow was up there. But even then, they'd have difficulty even copying or anything like that. Now, associative agnosias are a little more higher level. I like the one over to the right there where you got a cane and then a folded up umbrella, and then you got an umbrella. So you really got two umbrellas, and most of us could pick out the odd object being the cane. Now, if you look below that, you can see they can copy things. It's a higher level thing it's higher level than aperceptive. And then they'd have a hard time telling the difference between chips there and Scrabble, and hard time telling real animals from unreal animals. So this is an associative agnosia. Now, the next thing I want to talk about is called Prosopagnosia. And sorry, I'm skipping around here, but I wanted to go to this slide right here. Prosopagnosia is called face blindness. And these people cannot tell people's faces. And I read an article once where somebody with prosopagnosia said, it must be me. She's looking in a mirror. And she said, it must be me because I'm here. And this is Emily. And she said she could not bring her face back into her mind's eye. I really like that. Prosopagnosia cannot recognize faces. And now I can go back. I found this earlier today. Here's a woman who has a website. Her name's Cecilia Berman. And prosopagnosia is called face blindness. And so she says in her website, she says, well, now look at that rock over to the right and look at me. And then come up with a number of describable features useful for identification. And then you can go to the face, her face, and come up with useful features for identification. And then you can go over to that rock and look for features that are useful for identification. The thing is that if you have prosopagnosia and have a lesion in a certain part of the brain, you can't tell faces, but you can still tell the differences between different rocks. So there's an area, as she states. The answer is instead that the human brain has a specific center that does nothing more and nothing less than recognize faces. And this is in the Fusiform Gyrus. I'm going to show you where this is, but I thought this is a great website if you want to go and look at it. Now here, these are all she gave her friends names to different rocks, shapes, and she can remember the different rock shapes. She can tell the difference between the rock shapes because she's using a different part of her brain. When you have a lesion and you have prosopagnosia, you have a lesion in a certain part of the brain where it just results in you being face blind. And this is it again, okay? And this is the area where you have the lesion. And I like the one on the left better. You can see the ventral surface, and you can see the areas there that we call part of the ventral surface of the temporal lobe. The drawing on the right gives it numbers 36 and 37. But usually, sometimes it can be a bilateral lesion. Sometimes it can be unilateral. They used to think that the only way you got prosopagnosia was with lesions. But now they're finding that more and more people are going to doctors who were born with the problem. So prosopagnosia. Now I'd like to talk a little bit about central achromatopsia. Now, over to the right there, you can see one of the retinal cells that Dr. Ulrich talked about, a cone. And you know that the retina has cones that are sensitive to different colors. Now, we're not talking about a problem here in the retina where you would be receiving the color. We're talking about areas in the brain very near the area we talked about for prosopagnosia. So we call this central, that is in the brain, achromatopsia. And you can see it's very near the fusiform gyri that we talked about with prosopagnosia. So these are a couple areas that can result in it, areas 36 and 37. And I wanted to show you this. You can see that, what happens when you don't have color. And if you compare the top two, it's like night and day. And then you can see down at the bottom someone with Hemi Achromatopsia, where half the field is on the right is black and white and not very interesting, and while the left side is beautiful. So again, here's the fusiform gyri. So I guess you could say for any exam, fusiform gyri are damaged in achromatopsia, and areas very close to it or overlapping would be damaged in prosopagnosia. Now, you should know from Dr. Ulrich's lecture what an apraxia is. And it just means it's a higher cortical motor dysfunctions which affect performance and initiation of actions or action sequences, as well as the appropriate use of objects. So just think about apraxias as being, you don't have a paralysis, you don't have any loss of sensory information. You just, when asked, it's very difficult to initiate a movement. So that's an apraxia. Now I'd like to talk just a little bit about prefrontal cortex, because we're going to have a bunch of lectures on it. But you can see on my drawings there, area 9, 10, 11, on both the lateral and the medial wall. I've left white, and this is what I would call prefrontal cortex. In front of area 6, in front of area 8, in front of areas 44 and 45. So it's a huge area of cortex when you look at it. We call this prefrontal. This is the area of our cortex that's going to help us make decisions and, make John Harding what John, make me John. And as I said, Phineas Gage was one of the first prefrontal lobotomies. You can see the diagram up there. And you can actually see his skull there with that huge opening in the skull where the tamping iron went up through his orbit, took out most of his prefrontal cortex on both sides. So he has a first prefrontal lobotomy. Well, you can see the tamping iron there. And I like the picture of the young lady over there. I found that on the web. I don't know, it must be at a party or something like that. Well, if you lose your prefrontal cortex, all kinds of crazy things start to happen. I mean, before Phineas had that tamping iron go up through his prefrontal cortex, he was a law-abiding, nice family man, went to bed on time, got up on time, went to work on time, went to church on Sunday, and all of a sudden after, well, first of all, it's amazing he lived, and but he did live, and he was sitting on his front porch that night, and I'm sure they had to worry about infection and things like that, but, you know, he could see, and he could hear, and his memory was pretty good. I mean, he could move. The tamping iron went up through his prefrontal cortex, and he had a lot of things he could do. But what really changed was all of a sudden inappropriate laughter, emotional lability, disinhibition. You know, a lot of our prefrontal cortex is inhibiting us from doing kind of dumb, crazy things. Criminal behavior, unusual sexual behavior. So this is all no planning. He couldn't plan his future. He couldn't think about saving money, things like that. His future, he never thought about his future. Anosmia means he couldn't smell because the olfactory system comes in right under those prefrontal lobes. The other thing I want to say about prefrontal cortex is that we have our working memory up in our prefrontal cortex, and we're going to have a lecture on memory later in the course. And the working memory is just, from my working memory right now, as I sit here making this tape, it's everything in my head, everything in my mind right now. Some people might call it short-term memory. You know, kind of like I'm planning ahead about the next slide, but I've got some things in my mind right now, and that's my working memory. And I'm bringing up, a lot of those things are coming off the screen into my brain, but also I'm bringing up anything I might remember about this slide or about working memory. So working memory is like also called the chalkboard or blackboard of your mind. Things that are right there fresh up in your mind at one time. And usually this can be up to about 7 different things at the same time. So that's my working memory. And that's one of the most important things done by prefrontal cortex. This is also kind of cool in here to show you the different radiations of visual cortex. You can see that we're, you know, right up there in front of auditory cortex, you see Wernicke's and auditory, right up there would be deep, would be the lateral geniculate body. Now you've all had visual pathways, so you know coming out of the lateral geniculate body are fibers headed for area 17. And they can take 2 routes. They can go up underneath the parietal lobe where they can sweep down and around the inferior horn of the lateral ventricle and go to the ventral bank of the calcarine. The ones that go the top route go to the dorsal bank of the calcarine. And you should be able to, the bottom one is called Meyer's loop, and you should be able to take it from there. But you can see that a large lesion there, the parietal lobe, could interrupt that dorsal stream, and a large lesion of the temporal cortex could interrupt that ventral stream. There are also, when you have big lesions of your prefrontal cortex, usually bilateral, you have what are called frontal release signs, and these are certain reflexes that you had as a baby, or that you're usually trying to inhibit. These include the grasp, the snout, the root, and the suck reflex. And you can read this, but these things, when people have huge bilateral prefrontal lobe lesions, or in the case, say, of Alzheimer's disease that's completely demolished the prefrontal cortex, these frontal release signs come back. You normally don't have them. You might have had them earlier in your life when you were a baby, but then they're inhibited. But now when you lose that cortex and you lose the inhibition that cortex can do to certain reflexes, then all of a sudden they're back. So they're called frontal release signs, and this is pretty, you should know this. Finally, we're going to make a slice through here. You can see I've labeled something there in the middle of the slice called the hippocampal gyrus. And deep to this gyrus is the most important structure for memory called the hippocampus. And this is in your slides. You can also see, I like this little drawing of the hippocampus up here, this happy hippo. But you can see the hippocampus there. Some of you might recognize the cerebral peduncle, the pons, the nigrid, ruber duber sluber, the pretectum, posterior commissure, the pineal. You can see the lateral geniculate body looking like Napoleon's hat. You can see the medial geniculate body, and then down there just below and to the right on my screen is the hippocampus. And this is a structure that's going to really help us make memories. I call it the memory maker. There's a famous patient called HM who had epilepsy, and to get rid of the epilepsy, they took out HM's temporal lobes on both sides. They didn't know about the importance of the underlying hippocampus, so they took out both of his temporal lobes and his epilepsy went away, but he never made a new memory from the day of the surgery. So for instance, if I had a lesion today in my hippocampi bilaterally, I would never ever, I would never remember anything that happened to me after I had those lesions. I could live to be 100 years old, but nothing from my current day right here at the media center till I died at 100, I wouldn't remember. That's the hippocampus. Now,